My name is Steve Bauer. I'm with Cisco Systems. I've been with Cisco for almost 18 years at this point. It's amazing. And I have my first confession for today is I'm not here to sell you DevOps. Many people are in different phases of their journey, if they've even started at all. And what I actually wanted to share with you is some techniques that we've used at Cisco to help some of our cycle times and some of the productivity for engineering. So my bio in the conference notes says I've been an IT Linux Unix guy since the Bronze Age. And what I mean by that is I started out, we had some VAXs. Anybody remember VAXs? Good times, right? But they were running Ultrix. So, you know, first professional experience as a system administrator, I'm a Unix head, all right? Yeah, here we are, I'm having fun. And we had a fairly large environment at the time. This was before Cisco, a while back. And we actually had 5 VAXs. Like, ooh, this is a pretty big environment, right? And so I'm an IT guy, right? So we need to manage them, of course. One of the options we have, there are only 5 of them. We can go on, log in and touch each one. Anybody remember our login? More good times, right? Don't need to use a password. No encryption. It's great, nice and easy, right? But you know, with 5 systems, you don't necessarily want to log in, do your thing. What you can do is maybe consider starting a little bit of automation. So you can do something like a little shell script. I'm a Unix head, sorry, did I mention that? Shell script, here you go. So you can put your little list of hosts into a shell script, and you can say, for each of these hosts, do an RSH to it. Remember RSH? It's sort of the sibling command to rlogin. Just say, run a command remotely, that's fine. And you could do it, and once you've got this little script written, saved, and everything, you've automated something. You know, hey, all right, gold star. So this is wonderful. You've got 4 or 5 systems. I skipped 4 here because at that time, VAX 4 was actually running VMS, so I ignored it as much as I could. After a little time of doing that, of course, in every IT environment, things start growing. We added some VAX stations when they came out with those. Then we added DEC stations. Remember, that was a different processor architecture that they were using the MIPS chips and things. And so the environment starts growing a little bit. This little for each loop isn't really as fast as we want it to. We've got 50 machines maybe at this point. It takes a while to get through all of them. So one way that I figured we could make touching these systems by not touching them a little bit faster was to parallelize. So I wrote a little utility called mRSH for multiple RSH. I think many other people have probably implemented similar things over the years. And it would do multiple of these commands in parallel. So by default, I did 4, you know, 'cause I didn't want to overstress the system that I was starting these connections on. So I did 4 at a time. And when you get to 20, 30, 50 systems, great. 4 at a time. It reduces your total time to touch them all by roughly a quarter. So a couple examples, if you want to see how long they're up, what their load average is, use the uptime command, mRSH, the few of them, uptime. Look at that, this is cool. We had the ability to put a list of hosts into a flat file. Like Unix heads, we love flat files, text files. Everything is text whenever we can. And we'd say, hey, check for errors in the messages file. Remember when it used to be var ADM, now it's var log everywhere. Constantly trips me up, right? So the other thing that was sort of a sibling command to mRSH was mRCP, which would do multiple RCPs in parallel. And So with this, you could say, like, if I have a hosts.equiv file, which remember was that secret sort of permissions file that says people on this host can get into that host without a password, because we had no passwords, right? If I had an update to it, I want to keep it the same everywhere, I could just copy around a new copy all the time to all the systems in parallel. So cool, this is great. So we went from dozens of systems eventually to hundreds of systems. And this parallelism idea really served us pretty well. Last year at this conference, somebody presented this meme, automate all the things. And I wanted to extend that to, say, parallelize all the things. And that's that's probably one of the main things that has really served me well over the last halfway to forever that I've been doing this stuff. So eventually, I went to Cisco. And that was 1997. This is the back of a t-shirt that we had made around 2000, I think. And the group I joined in Cisco was called Engineering Compute Services, which was the little branch of IT that was dedicated to providing engineering infrastructure. The Unix, mostly Solaris at the time, servers that they use to develop iOS with the big I at the beginning. And at the time, we were kind of a total soup to nuts shop. We managed the users' desktops, many of them Sun workstations, some of them Windows systems, some Macs even at that point. And we also managed all the networks, both the desktop networks and the data center networks. And we had a bunch of data center servers. We had 720 servers at the time of this printing. And we managed all the systems in 5 countries. Here, East Coast, West Coast, we had some. In India, I think at that point, we had Canada at one point, and it's hard to remember all of them. But one of the interesting things that is, I think, fairly unique to the way we did and do things in ECS is we have an environment defined where we install a standardized OS image that pretty much everybody uses. And whenever a group has tools that they need to install that aren't part of the OS or are a different version than what comes with the OS, they would install it into an NFS area. And so each different group may have their own NFS area, all accessed by the automounter. We live and die by the automounter. You want to talk about automounter, well, we can. And so that really helped us scale a lot. Being able to deploy systems with fairly minimal customizations in most cases, and let people from many different groups start working on them. So one of the things, given the size of the environment we have, I needed to bring over this MRSH capability. So the original version was written in C, because that's kind of what you did in 1980 something. And so I rewrote it in Perl, and this it's great. And as you grow more and more, we started doing things in greater batches of parallelism. At 1,000 systems, we might do 20 to 50 in parallel. You can read the numbers. At 20,000, a lot of times I'll use 1,000 plus processes at a time to talk to them all. Sometimes if I'm feeling crazy, I'll do 2,000 or 3,000, but not all that often. But the servers can handle it, so it's great. A couple of things that have been driving this growth that we've had. First was an effort to move off of the old Sun servers and into commodity Linux hardware. The Sun servers, we frequently had from 10 to 75 or 100 people on one system. They took months to acquire and deploy, lots of power. You know the drill, right? Get out of the big stuff, get into the little stuff. And so we created this service called the Linux Development Service. And what that was we had racks and racks of these pizza box Linux systems. And when a developer needed to start doing some development work, we had a little portal for him. And he would log into it and say, hey, I need to do this and this, I need this OS version or whatever. And we would pick a Linux system for him to log into. Now, this was early days for virtualization. And remember, I'm an IT guy for engineering. And engineers constantly complain about how fast or really slow things are. And so at the point that we were starting to deploy this service, we tried virtualization. It was just too slow. You know, engineers are going to notice a 50 to 100% build time hit. Right, so that was out. So we deployed this on bare metal Linux servers. And so we would take one of these servers and put 2 to 4 to 5 or so users on the server. And remember, the Sun systems would take a month, 2 months, 3 months to get in. What we did was we were able to pre-stage a lot of these Linux systems. And when the user made a request, we cheated. No, we optimized. We had the systems pre-configured already, up and running, installed, waiting for users. And when they said, give me a system to develop on, it was already there. We just pointed them at it. So we were able to say, you know, hey, look, we've got 15 to 30 minute provisioning time on bare metal systems, but it wasn't provisioning. It was allocation. This is great. At its peak, this service ran about 1,000 to 1,200 Linux systems worldwide. And we started it probably 10 years ago, maybe 8 years ago. Never remember anymore. And we pretty much phased it out about 4 or 5 years ago. Now, what's taken the place of the Linux Development Service is the Aurora project. One of the things we saw with the Linux Development Service and these bare metal systems was some systems were severely overloaded if the 3 or 4 people assigned to it happened to be all doing their software builds at the same time. Others would be pretty much completely idle, as people were off doing other things, or they had created a system and never really just got around to using it. So in an effort to sort of normalize our infrastructure and get away from the waste of all these physical machines and really make things more efficient, we moved to this virtual machine capability. Some of the features that we have are, in this situation, now these VMs are actually provisioned on demand from the user. So we've got another web portal that we started. It looks very similar to the original one we had for the Linux Development Service, but you make the request and it actually provisions the system from scratch for you. It has a configuration agent inside the VM that performs the integration work to get that VM to talk to all of our networked resources in the company. The auto monitor configuration, originally NIST+, now AD for authentication, all those things. Anybody use ClearCase? Remember ClearCase? Sets up the ClearCase region for the user. And one of the features of it is this flexible storage. When we started with the Linux Development Service, we had these pizza boxes, and we made the disks in those pizza boxes available to the users to store stuff on. We called it no backup. Can anybody guess why? This is not backed up. In the old days of the Sun servers, everything was backed up. Oh my God, expensive, but everything's backed up. So we really needed to reinforce to the users that this stuff is not backed up. So we carried that forward. We're not backing up these VMs either because it's still, oh my God, expensive. And we're making sure that people know this is not backed up. Message of the day says, only put stuff here if you can recreate it easily if it's lost. In the VM environment, we don't lose stuff from no backup very often as a function of the infrastructure changing because it's all enterprise storage underneath, all that good stuff. But an errant RM can delete it and it's gone. But the flexible part of this is something that we were able to do since it's a VM. If you allocate a VM, and say you start it with 60 gigabytes in this no backup space, and in a week, a month, whatever, you decide that, hey, I need to start work on a second code base or pull a second code tree, and that 60 gig isn't going to be enough. You can go back to the web portal where you requested it and say, hey, edit this VM, give me 100 gig, 120, 150, 200 gig, if you like. And this is something that I'm really proud that we got it working. It can do it online without any interruption to the user. And if you time it right, you make the request, in a minute or so, you can do a DF to watch the size of the file system growing while you're logged into the system. That's cool. I got to bring it up every time I can. So this Aurora service has an architecture, a number of pieces that make it up. The names don't really matter all that much, but what really matters to the users is first, come in and make a request. Then the process flow goes through all this stuff in between, and eventually a virtual development system is created. It has this storage. It could be some LUNs or what have you. It's put into the no backup for you. And then to the user, step 2 is start developing. Log in, pull your code, and do your work. This is pretty cool. I like it. We first deployed Aurora about 5 years ago, I believe, and went into wide-scale production about 4 years ago. At this point, we've got about 9,000 VMs total that end users are logging into. About 6,500 or so actual users using it. So people are creating multiple VMs, which is cool. If you've got things to do that requires another VM, that's great. Different location if you need it, or different OS version if you need it, that's great. It's in all these different locations. Our biggest site, of course, is San Jose, right? This is Cisco at San Jose. About 4,500 VMs there, about 3,000 in Bangalore, and then the rest are in those other green sites. There are some other data centers up here that we, as ECS or engineering IT, support. The gray ones are ones that we don't have Aurora in right now. So this has had a really good effect on our engineering environment. And so the general benefits of this are we've got the flexibility to give people resources when they need it. We've increased our density and reduced our compute footprint, which saves us, not only money buying computers, although we do give ourselves a fairly good discount on our own hardware, but power and cooling and data center space. This is terrific, and faster performance. So I think a couple of you are a little bit puzzled about this. We went from bare metal to virtual machines, and we've delivered faster performance. How did we do that? I said that virtual machines were slower, didn't I? And this is where ElectricAccelerator comes in. So what ElectricAccelerator does is it takes your build and it divides it up into all of its component steps and sends those out to a cluster of nodes. I've got a little picture of it in just a second. But with ElectricAccelerator, we were able to match and beat the performance of these bare metal systems that people are moving from, putting them into a VM. And now the horsepower inside the VM really doesn't matter anymore because it's not really doing much. It's sitting there waiting for you to type. It's saving your editor files. And when you run your build with Accelerator or Emake, all of the actual processing happens out on the cluster. So this is cool. Here are some results. You're not going to be able to read this, which is fine. Along the x-axis is just a list of a lot of the images that people have built using Emake. And it started with some of the first attempts all the way on the left So it's sort of chronological. And those first couple tries, we didn't really focus on making sure things worked the best they could in Emake. But over time, we got much better results with things. And that really big pair of columns near the middle are 10-hour builds that went down to about 2.5 hours or so. And I can't even read the thing to say, oh, that was UCBU. That was a call center, I believe, piece of software. So this is cool. So what does ElectricAccelerator look like? And I stole this graph, this chart. It's an old copy. I see some of the Electric Cloud people sort of cringing. It's like, ooh, Steve, you got to update. But you know, it was handy. What can I say? And so if you don't know much about Emake or ElectricAccelerator yet, first sort of ignore that red box on the left. That's Electrify. I figured as long as I'm stealing the slide, I may as well deface it while I'm at it. So underneath that is really Emake in the original. So on the left-hand side, you've got your developer machines. When you want to do a build, you run Emake. It analyzes your dependencies, figures out which commands I need to perform, and it sends those commands off to your cluster that's on the left-hand side of the screen. And so when it says I need to do these 2,000 compiles, those will happen off on the cluster. And one of the neat things that it does for you is it handles data access for you transparently. So when GCC, for example, runs on this agent node on the right-hand side, it says, I need to open foo.c. They have this electric file system underneath that says, okay, a user process is requesting foo.c, and it goes back and talks to the original Emake on the node where you've invoked your build, where you're doing your development work, says, hey, give me Emake, give me foo.c. It sends it over. The compile continues on. Hey, I need foo.h. Same thing, goes back, sends it over. And so on and so forth. When that compile is done, you get foo.o, the object file from it, and it sends that file back to the Emake system where you ran your build, where you started your build from, and it writes it to your workspace. And this is great. You get the offload capability, you get the file access handled for you. And another key feature, I think, of Emake when you use it specifically as Emake for builds is dependency management and dependency tracking, really. Since they have this file system underneath, they know exactly which files your build is accessing. So it can tell if you have, they call it implied dependencies, I call it broken dependencies, because I'm not as nice as they are. If one job depends on a specific file, and that file is created by another job, if you don't have in your make files something that expresses that relationship, your build can break if you do it in great parallelism. Right, so the parallelism can increase the risk of race conditions that will break your build just due to these missing files or out-of-date files. So with this knowledge that they have of the real dependencies of the build, Emake can go in and dynamically fix them for you. Well, not really fix them. It doesn't update your make files, but it works around them. It tracks for itself, hey, I can actually make this build work by doing this first instead. So that's great. That's Emake. There's a lot more to it, but that's probably good enough for now. The piece that I've really been most taken with is Emake's little brother, I say here, Electrify. And that's, I could have made it graffiti, I guess, if I wanted to, but who has the time? So Electrify has a lot of the same capabilities that Emake has. It's sort of a general command farming or clustering type of capability. So if you tell Electrify, hey, I want to run a command out on the cluster, it will send that command out to the cluster, and it will perform that same file transfer transparently stuff for you. So you can use it for a lot of fairly interesting things. Use case number 1. This is me sort of playing around. I actually happened to read the Emake documentation. I know nobody reads documentation, but I don't know, I was bored, I needed to sleep, who knows. I have this MRSH, MSSH, remember that? RSH became SSH. So of course my little multiple command invoker had to adjust. SSH, all right, we're secure now, yay. The other capability it has is this mdo personality, and that is sort of a generic parallelizer. And my example here is using it to compress files. Now I've been a Unix head for forever, right? And one of my big focus points is performance. Engineers come to me and say, hey Steve, why is my build so slow? That's a very nice way of saying it. It's not always nice. But they, what I need to do is do my own build experiments. I run their builds. I do a collection of statistics, VM stat, IO stat, SAR, all that good stuff, the standard Linux performance metrics tools. And I run so many of these builds, testing out different system configurations, different underlying hardware, different storage, that I get an awful lot of data. So I need to compress that so the storage guys don't kill me, right? Because I'm using tons of storage. So I've got this mdo, and why don't I compress this stuff? So if I've got an 8-core system, I'll use my little mdo thing to run 8 compresses at a time, -C8, 8 children. The file names I'm going to give it are big star, and the command I'm going to iterate on each one of those is gzip to compress them. So mdo does the same thing that MRSH and MSSH did, runs them in parallel. And this is great. Another utility that can do this, it didn't exist back, or it didn't have this capability way back when, is xargs. That can take a bunch of things on the command line and run a command on all of them. This is an equivalent command, effectively, with xargs, echo big star, pipe to xarg, say give these subcommands one of these input names at a time, and run 8 of them in parallel. So here's another potential way to do this parallelization without using my utility. I happen to like mine better. I've a little bit of favoritism, but that's okay. So we have Electrify. We have this little parallelization capability. Let's throw them together. And so this is a way that you might use Electrify to take these gzip commands and put them out onto the cluster. And the exact arguments, I'm pretty sure this is correct. You can try it at home, but it's not completely tested. You tell Electrify that, hey, whenever you see a gzip command, send it out to the farm, out to the cluster. And so Electrify runs this sh command. mdo is running 32 of these gzips at a time, so when Electrify sees those gzips, it'll send them out to the farm. And this is sort of a diagram of how it looks. So this is great. I can do all of my compute-intensive processes in parallel. The input files that I'm compressing get automatically sent out to the farm. The output files that have been compressed get brought back to the system where I've run my mdo. Electrify has this sort of underlying capability for Electrify proxy, and the previous example uses I think what they call automatic process interception. We have a fair amount of old tools. We're running 64-bit systems, but some of them are 64-bit tools, some of the 32-bit tools, and that can cause this automatic process interception that Electrify does to have some problems. So to be sure about what actually goes out to the farm, you can tell it, only send things to the farm that I explicitly tell you to with this Electrify proxy process. So this is just an adaptation of the same thing we just did a minute ago. And we tell it Emake Electrify is none to say only do the explicit things. And then under the mdo command, we say Electrify proxy this gzip. So that looks pretty similar. Oh, we missed a couple Y's there, that's okay. So mdo invokes these Electrify proxy commands, and having invoked that, Electrify proxy causes those commands to be sent out to the cluster. Cool, this is great. This is how it really works. Now let me go back a second. I have Electrify proxy telling the agent node on the cluster, hey, run this gzip command. But that's not how it works. And remember, I'm a Unix head, sysadmin type. I care about these things. You may not. Here's a picture anyways. So Electrify runs mdo, just like we saw in the previous example. Mdo runs Electrify proxy, which is great. But Electrify proxy doesn't actually talk to the cluster itself. It talks back to the top level Electrify process. And then that Electrify process causes your command to be run out on the cluster. And this makes a fair amount of sense because this top level Electrify process talks to the cluster manager and says, hey, I need this many agents, or this many cores, effectively, or I don't need these anymore. And it manages the pool of where you can actually send jobs. So having this Electrify proxy talk through that makes that work, and makes that really happy for managing the cluster underneath your session. So feel free to ignore this. Let's move on. So we talked about, this is my stuff so far. My own playing I've been doing for my own nefarious purposes. Real world case number one. We have these Emake clusters in all these different Aurora locations. And I got a call one day. Well, it started as an IM, right? But you can never have some of these conversations in IM, so we talked on the phone. I know it's horrible talking on the phone. But Jerry David is a guy who's here in San Jose. He wanted to buy a bunch of bare metal Linux systems. And what his users were doing was this firmware analysis, which the firmware developers would build the firmware. Then they would have to run these 200 checks against it, sort of a regression testing kind of thing. Not completely clear on the details. It doesn't really matter, thank goodness. But they would have to run 200 of these things. And they already had a little parallelization capability built into their wrapper script. If you have a 6-core VM, 8-core VM, or whatever, it could run 6 or 8 of them in parallel. It still took two hours. Each one of these things might take 20 seconds up to 15, 20 minutes. But for the 200 of them, 2+ hours. And so he wanted to buy a bunch of physical infrastructure to be able to sort of write his own farm these jobs out someplace capability. And we're talking on the phone, and I said, hey Jerry, guess what I have in my back pocket right here? We've got Electrify. So we did some experimentation, and his script that does this parallelization is called echeck. And so the way he figured out to get this working under Electrify is he had echeck to call Electrify and told it to call echeck itself again. And so this got an instance of echeck running under Electrify such that it could then perform the parallelization out to the build cluster. So it was able to run Electrify proxy to tell it to run this check, and it would send those jobs out to the cluster. And our default build agent allocation is 32 agents. And he said, hey, what would happen if we did this on 200 agents at once? I said, well, you'd probably get 200 agents, at least in some of our locations. San Jose, of course, the biggest. But we can try it. Sure, why not? And So we tried it with 200 agents, and it went pretty well. Our 2+ hour test time for these developer builds came down to 20 minutes. And this is terrific. This is fun. Another interesting thing about this particular use case, let me go back to the diagram again. Remember, we have the developer system on the left side of that architecture diagram, which actually kind of lines up here, which is really convenient. On the right side, you have the build cloud, or the build cluster nodes. In this particular situation, the checks that he's doing are fairly CPU intensive, but not very I/O intensive. So what this meant was that he was able to separate the eCheck run itself from the build cluster geographically. So even though our biggest cluster was in San Jose, there was people in Raleigh or wherever else, they had smaller clusters. They were actually able to run their eCheck in RTP and tell it to use the San Jose cluster. So it could get 200 jobs in parallel using San Jose, and the back and forth of doing file transfers was fairly minimal. So he got a very good benefit being able to do that. So we didn't have to grow all the clusters globally for them to be able to do this. That's pretty cool. If you want to do that, you're going to have to try it yourself. Depending on your specific workload, if you have too much I/O traffic, you probably need to keep your cluster co-located with where you're doing your build, or where you're invoking your processes. So that's use case number one. The future directions for it, they're up to 500 checks now. Testing requirements keep on going, especially when you add a second architecture. It's like, oh, I got to do all the same tests for 2 different CPU types. Great. So they're working on doing that, and they're also implementing adjustable parallelism, and this is done by Steve Johnson, who is down in RTP. And what that does is it takes a look at the cluster that it's being sent to and says, I'm not going to use more than 40% of the cluster myself. So if I have a nice big cluster like in San Jose, I can use a whole lot of agents, but I'm going to scale myself down a little bit on smaller clusters, and I'm going to keep an eye on the cluster and maybe grow my parallelism or shrink it if other people are starting to use it. Real world case number 2 is a little bit smaller. We had some people who needed to do some ASIC simulations. I forget the exact tools, but the simulations to make sure that your ASICs will print up properly and not overheat and all that good stuff. And they were based in the UK, where we happen to have an Aurora system, Aurora installation. And most of the other engineers in the world who do that kind of thing will use a dedicated server farm just for simulations. And they use a management system around that, some sort of load sharing facility or something named after that. But it was a very small user base here in the UK that wanted to do this. And they really didn't feel it was worth setting up all that extra infrastructure to just run the 20 or 30 simulations a week they needed to do. So we have an Aurora location where they are. We have Emake there, Electrify. And so they were able to use Emake and Electrify, depending on the test they were doing, to perform their simulations just out on the accelerator cluster. This is great. We didn't need to buy anything. We didn't need to license any additional software. We saved some money. Isn't that great? Real world case number 3. One of our code bases, remember iOS with the big I, there are several flavors of that. If you're familiar with their products. I'm not all that familiar with their products. I just know the names of some of the projects here. iOS XR. It was created a number of years ago, and they use a tool called ejam to orchestrate their builds. Now you're familiar with Make. It's another thing that's not Make that can do basically what Make does. And it has a few extra features that might steer you towards using it. And this is fine. But the thing is that ElectricAccelerator doesn't have a personality for jam. It supports Make and Ant, maybe a couple other things. I forget. All I really use is Make. But it doesn't know how to do anything with jam. So I was talking with some folks who own some of the jam build infrastructure, and they were talking about how they were sort of experimenting with doing some build offload kinds of things. And jam has this little setting in it called jam shell, which tells jam, hey, if you need to run a command, a compile or something, instead of using the standard system shell, use this other command that I'm telling you to use. Guess what we can put in there? We can put Electrify in there. Now this is a little bit more complicated use case than we had previously. And these are the components that we had. And this is really just an experiment I did. Let's see what we can do. So in the middle we have jam. That's still required as the orchestrator for the build process. At the top level we have ejam, which I created, just a little wrapper, kind of like the previous guys have their wrapper to do the simulations that they did. It sets up the environment, sets that jam shell environment variable. The ejam wrapper runs Electrify, which we know at this point. Electrify is told to run jam. And before I invoke Electrify for jam, I set this jam shell environment variable to ejam proxy. Because jam doesn't always give you exactly what a shell would like to get. I'm not sure how it works, but when you specify jam shell, things look a little bit different than you think the shell would really be happy with. So we need to process it a touch before we can send it out to the cluster. So hence ejam proxy. And then underneath that, once ejam proxy has said, all right, this command is ready to go out to the cluster, it will run Electrify proxy. That's a lot of stuff, isn't it? So here's the diagram of that. And it's not all that different from what we've seen before, just a couple extra pieces here and there. We've got ejam, runs Electrify to run jam. Jam, when it says I need to do this compile, that compile, that compile, it runs ejam proxy. Ejam proxy says, okay, here's how we send this job out to the cluster. It invokes Electrify proxy. And lo and behold, that job gets sent out to the cluster. Again, with all that same file transfer stuff happening for you automatically. This is the type of thing that these jobs are fairly I/O intensive. C files, header files, C++ files, all sorts of things. This is not the kind of thing that you would want to have your user in one location and the cluster in a different location. These are the kinds of things where your latency needs to be fairly quick. But this worked. Like, oh my goodness, look at that. I'm just playing with it. And what we got out of this was a 50 to 60% time savings on this build. Now, one of the drawbacks of doing it this way and not using Emake is that, remember, Emake has that automatic dependency tracking capability because Emake knows what the dependencies are, because what the dependencies in the make file are, because it's reading your make files to decide what steps to take. With ejam, it's still just the regular jam that's doing all that dependency calculation. So if you have missing dependencies or implied dependencies, you need to fix them yourself. Electrify can't come to your rescue for that. It expects whatever is doing the parallelism to know 100% what can be run at the same time. It doesn't always work that way. We know how it is with decades-old code bases. And this is one of those situations where increasing the parallelism has caused some race conditions to come to light with some build failures. We managed to find many of them, enough of them to get a number of builds working. So we're working on some further reliability issues, always getting more broken dependencies in the code bases. But 50 to 60% time savings, the way the electric cloud guys tell it, is 2 to 2.5x build acceleration. Just flip the ratio. So this is cool. So today we talked about some of the reasons for starting to do some parallelization and some of the successes and things we've done with using ElectricAccelerator and really Electrify in our environment to help people do things. So that is basically what I've got for you today. I'm happy to take any questions if anybody is curious. We have a few minutes at least. Okay. Oh, one question.
How do you think about the time saved and what you do with it? Are there times when absolutely you get the full amount of savings, or you feel like you get a portion of it? How do you think about that for your developers? So many people using it.
So the question is, how do I think about the time savings that we're getting? Are we getting enough time savings, or
No, what do you do with the time?
What do we do with the time savings? The expectation is that the users will be able to do more development cycles. You know, if my build takes half of the time it did before, I can do more builds in a day and do more of the edit, debug, compile, whatever order that happens in processes. So the goal here is always to make our end users as productive as they can be. So that this is one step to doing that. Cool. All right. Thanks very much. Go get some lunch.